All right, back again. Have the probe hooked up. This is the first in 3 tests showing the waveform on the signal input to the RF unit, which is where the signal gets heterodyned with the VCO to produce the signal which goes into the driver, and then of course the driver into the power amplifier. I have the driver tube powered down, in other words, no filament lit. I also have the power amplifier powered down, no filament. We don't need it for these tests, so that is all turned off, as you can tell. Have it hooked up here. Please don't anyone yell at me for my method of hooking up cables. It's what I have available. Anyway, that red line is the signal line. That basically would be the driver line for whatever signal is being produced at the mic after all the various audio processing is done. Now that signal is modulated, or I shouldn't say modulated, it modulates a 8.9 megahertz signal, which is then heterodyned with the VCO. So we're just going to do 2 simple tests here. We're going to, I have it on 40 meter right now, and then I'm going to show you on 40 meter. I'm then going to turn the carrier a little bit, the carrier knob, to show that the signal does variate. It does change amplitude. And then I'm going to turn it to 20 meter. And it doesn't make any difference, of course, changing the meter from 20 to 40 or 40 to 20, because all that's doing is changing the final output of the final frequency, which is going to go to the power amplifier. You know, go to the driver and the finals. So basically all that does is change the VCO, the voltage controlled oscillator. So in a way of proving, the important thing here is that there is no variance at all in the amplitude, within reason of course, between 20 and 40 meters. And the waveform is fairly stable, or I think it's quite stable. So anyway, I'm going to center on the scope right here and get it, I'm doing this with one hand, so I hope you all can see that all right. I don't know if that's legible. I do have a frequency printout, and I have a peak to peak. Anyway, here we go. This is on, let's see, this is on 40 meter. Vary it a little bit, see? Now, of course, the important thing is note where the waveform is. Now I'm going to change it to 20 meter. Okay? And we'll do the same exact thing. You notice that the amplitude is exactly the same, and the waveform is very stable. And I don't know if you could make out the frequency or not. It's basically dead on. It changes a little bit because you know, this oscilloscope is not really made to be a frequency counter for that. I really should use this, but I don't need to. There's nothing wrong with it. Anyway, on any band, it's going to show 8.9 megahertz because that doesn't change. The important point of the test here was the stability of the waveform and the amplitude, which you can tell there's no variation between 20 and 40. As I said on the forum, there is some ALC being produced on 160, 80, and 40, and a little bit on 10 meter. It's really bad on 40 to the point where it just attenuates everything down to almost nothing. The reason I'm selecting between 40 and 20 is because there doesn't seem to be any ACL activity on 20 whatsoever. So I'm trying to take a juxtaposition between 2 extremes. And as you can tell, there's no difference between the waveforms coming off of this signal line. So that pretty much passes as far as I'm concerned. Alright, so the next video is let me change the wiring, and I'll show the VCO. And then after the VCO, we'll show the actual RF coming out of the unit itself. Okay, thanks. That didn't take long. As you can tell, I have the connection now on the yellow line, which is the VCO line. we don't even have to depress the tune button here because it continuously produces VCO, and of course it doesn't make any difference what the carrier is on. I have it on 40 meter band now, and this is what we're getting. All right. Off the top of my head, I don't really know what it's supposed to be. I think it's supposed to be about 15.9 megahertz. I have tested this before and just kind of take my word for it. The frequency is correct, and it's really irrelevant anyway because, well, it's not irrelevant, but that's really not going to be causing your ACL problem because provided that the waveform is stable, no matter what the frequency is, it shouldn't be kicking the ACL all over the place. The ACL only should be worried about peaks. And that's the dilemma here. But anyway, you notice the waveform. We're doing a sample at 2.5 gigasamples a second. And it's 200 millivolts each large division. And we're getting a peak-to-peak of 688 millivolts. Very stable. Amplitude's fine. Now let's switch. That's on 40 meter. Let's switch to 20 meter and see what we get. There we go. Now, the amplitude has gone up a little bit, but the waveform is very stable. I checked the frequency tables. It is where it's supposed to be. The peak-to-peak is a little higher on 20. But what's ironic is that, okay, fine, it's driving it a little harder, or at least you would think, maybe. Well, that's all great, well and good, but on 20, we're not getting any clipping as far as the ACL is concerned. So that kind of rules out the VCO as well. As you can tell, very stable waveform. I don't think there's any problem here at all. Okay, so what we're going to do next is we're going to look at the output of the RF unit itself after it heterodynes these signals. Okay, bye. Okay, back again. I had to turn the unit around to take off of pin, what is that? I think it's pin 6 if I'm not mistaken, right there off of the RF unit in the back to get the heterodyne signal. I have it set in a pre-select matters now because you're tuning the circuit into the driver, excuse me. I do have it set up as before. I had it DC coupled. Now I have it AC coupled on the oscilloscope. There is a 10-volt bias, positive bias, when the signal is off. When you're tuning it, basically the bias goes to 0. I don't know why that is necessarily, but I don't think that's important right now. So I do have it. AC coupled, and I do have it tuned. This is 20 meter, okay, with it heterodyned. Now, as you can tell, that it's a little raggedy, but still, you know, somewhat okay. All right, now I'm going to change it to the 40 meter, and we're going to then tune it. Now, this might take a little bit to get it tuned up properly. All right, let's see. Let me, I'll be right back and tune it and then come back. I have it tuned up for 40 meter, and here is what I'm getting. And this is the interesting bit. You notice the waveform, how jittery it is. And I'll do that again. All right, so that's what I'm getting. Next, I'm going to show the RF, and then we'll go from there. I have it tuned up on 40 meter, and here's what we're getting. Nice, super stable waveform. Peak to peak, 2.3 volts, around 7 megahertz, which is exactly what it should be. Let's see here. Anyway, there's a lot of filtering that takes place after the output of that RF unit. So there could be some filtering to make the waveform as clean as it is. Anyway, that's on the 40 meter band. That's what's being transmitted. Now, I'm going to switch to the 20 meter band. This might take a second. Just give me a second to tune up here. Okay, let's see. Let it cool off a little. And here's basically what we're getting on the 20 meter band. Again, 14 megahertz, looks nice and clean. So I'm going to string all these videos together and post them, and I hope it makes some sense to you all. I'll do the spectrum analysis maybe tomorrow and post it. You know, the main question is that jittery waveform at the end. My hypothesis is that the waveform being jittery is actually causing spectral energy to be distributed amongst various frequencies, which are somehow interacting with the ACL. That's my working hypothesis at this point. Anyway, I'd like to hear from you all. I hope it doesn't sound too stupid what I'm saying. And if it does, well, I guess that's just me. Anyway, let me upload these videos, and we'll edit them all together. And I hope you all have gotten something from this. Bye.